Okay, continuing on, looking at integrated rate laws, there's kind of a special case primarily for first order reactions where we can define a time in which half of the sample reacts, called the half-life. This is pretty common for nuclear decay reactions, radioactivity producing reactions in particular. They're generally defined by the half-life, how long it's going to take for half of that sample to undergo whatever radioactive decay reaction is consistent with its structure. Now, if you think back to first order reactions, we had a version of the first order reaction integrated rate law where we had the concentration at time t divided by the concentration at time 0. So this version, natural log of concentration of R at time t over concentration of R at time 0 equals minus kT. Now, if you plug in 50% here, so half the sample is gone, 50% would correspond to 0.5 here for the ratio without the 100 and the percent. Natural log of 0.5 equals minus kT. If you take the natural log of 0.5, you can get an equation relating that time. So t with a little subscript 1/2 would be the half-life. How long it takes for half the sample to have reacted is equal to 0.693 over the rate constant. So this, of course, can be rearranged to have the rate constant equal to 0.693 over half-life. In fact, that is usually a little more useful in the types of problems that we'll see because you're often given the half-life, but you need the rate constant to solve the problem. So this will throw just a little extra step into some of these calculations where we're given half-life instead of given the rate constant. So watch out for that. And this is an example of a place where we will use the half-life. So radon 222 is produced by natural sources. It can build up inside a house if the right kind of environment is underneath the house in terms of the composition of the rocks. Radon, this form of radon has a half-life of 3.8 days. Right, if we assume the gas is trapped in a basement and can't escape, so the only change to the concentration will be the reaction happening. We're given a concentration here. Now, in this case, it's not molarity, it's atoms per liter. This is perfectly fine to substitute in for molarity. We know moles and atoms are just related by Avogadro's constant as well. But if we plug in atoms per liter, then the other concentration we get out at the end will also be atoms per liter. So we're given an initial concentration and we're given a time, 30 days. And what's a little different here is we have the half-life instead of the rate constant. So the first thing we should do is solve for the rate constant, because then we can plug into our equation for first order integrated rate laws. So 0.693, which again comes from natural log of 0.5, over the half-life, 3.8 days, will give us the rate constant. So 0.693 divided by 3.8. Our rate constant will be 0.182, and that will be reciprocal days, or per day, as our unit. Now, from there, we've got K, we've got the initial concentration up here, we've got the time. We can plug this into the integrated first order rate law that we've talked about before. So the natural log of the concentration at time t minus the natural log of the concentration at time 0 will equal minus kT. Right? And if we plug those in, and again, I'm going to use x for what I'm solving for. So we're solving for the concentration at time t. This would be the natural log of x minus the natural log of 4.0 times 10 to the 13th is our initial concentration. That's going to equal minus times k, which we just calculated, 0.182. And I'm going to leave the units off once I recognize that they match per day, and our time is in days. So times 30 days. Now the 30 there is only 1 sig fig. I'm going to make it 2 just so we're not rounding to 1 at the end of the problem. We'll round it to 2 when we get to the end. So once we get here, again, this is a math problem. So let's start simplifying and plugging in some of the math. So a natural log of x minus So we take the natural log of 4 times 10 to the 13th. Power is 31.32. And that's going to be equal to, multiplying out on this side, 30 times 0.182. So that with the negative sign, minus 5.46. So I'll add 31.2 to each side of the equation here, and that will give me the natural log of x is equal to 25.86. To solve for x, I again need to do kind of the opposite of natural log. So that would be, come up a little bit here, x is equal to e to the 25.86. And I'll plug that in. So e to the 25.86 is 1.7 times 10 to the 11th power. Now again, the units are going to be the same as what we plugged in, so this is not molarity, but this is atoms per liter of the radon that was our reactant. Now we could change that to molarity by using Avogadro's number, but that's not what's requested in the problem. It's just what is the concentration. So that is our answer. Now we can check, and we should check, that the answer makes physical sense, just to clear up that we didn't make a math mistake along the way. We started at 10 to the 13th. We're down to 10 to the 11th. So the concentration has gone down. So at least in that sense, we are correct in, at least in the direction of how we solved the problem. Okay. Now, the last kind of part of this chapter that we want to look at is called collision theory. And it's really trying to kind of work out how a reaction happens. We know in a reaction that some bonds are broken, some bonds are formed. The rate law tells us some information about how that's happening. And what we want to do is kind of relate the rate law to this sort of mechanism of the reaction. Like, what are the steps? Which molecules collide with each other? Which bonds break, which bonds form, and kind of in what order. And we'll kind of see how we can do that. One of the things we want to do there is kind of get an idea of sort of a pictorial representation of the reaction called a reaction energy diagram. And this will help us kind of visualize what's going on, but also maybe make sense of some of the information we get from a rate law or from a mechanism. So basically we have energy on one axis, and we have what's called reaction progress on the other axis. And that means we have starting materials. So I'm just going to use SM there for starting materials, right? What did we start with? What are our reactants? And then on the other side, we would have our products. Now, there's some thermodynamics involved here, depending on whether the starting materials or the products are higher or lower in energy. That's something we'll talk about in a future chapter in a little more detail. Right now, what we're focused on is what happens in the middle. How do we get from one to the other? That's related to the kinetics of the reaction. And in particular, we want to think about this quantity here, EA, or activation energy. And we can think about this in terms of what is known as the Arrhenius equation. The Arrhenius equation looks like this. The rate constant for the reaction is equal to capital A, we'll talk about that in a second, times the exponential to the power EA divided by RT. Now, R is the gas constant here, T is the temperature in Kelvin. A and EA are the new things that we want to think about here. A here is called the frequency factor. And it really relates to how likely a collision between two molecules is to result in the reaction we're considering happening. So if the first step of reaction involves forming a bond between two pieces, well, that bond's not going to be able to form unless those molecules collide in a way that those two atoms get close to each other. So if one molecule is kind of facing the wrong way and the two molecules collide, well, the reaction's not going to happen. So we can kind of calculate how likely that collision is from the other pieces of information here. But the one that's most useful for us here is the EA. in this case, which is the activation energy. Basically, how much energy does it take in order for a step in a reaction to happen? So if we just consider kind of a one-step reaction, the activation energy would be the energy difference between where we started and kind of the top of this pathway through the reaction. So this sort of hill that I drew in here is the pathway of the reaction. It is, in terms of energy, what has to happen to the reactants or the starting materials in order for them to become products. And we'll see these get a little more complicated. Most reactions are more than one step. The height of these hills will relate to what we can understand about how a reaction happens. Okay, and then real quick, to finish up this page, I mentioned catalysts a few lectures back in terms of they can speed up a reaction. And what a catalyst actually does is it changes this pathway between the reactants and the products. So looking at a reaction energy diagram, and let's say it's an uphill reaction this time where the starting materials are lower in energy than the products. Normally, a reaction like this would have a fairly substantial activation energy, right, to get to the top of that hill, which means we have to go over that hill in order for the reaction to happen. So that's uncatalyzed. And what a catalyst does is it basically lowers the energy of this top of this particular hill. So a catalyzed reaction might have a completely different pathway, and maybe the reaction doesn't have to go to anywhere near as high of an energy anymore. So the catalyzed reaction actually has a different pathway that gets us from reactants to products. Now, notice the energy of the reactants, the energy of the products are still exactly the same, but we may be able to get there with a little less energy. So the catalyst is going to help the reaction go faster or help it happen at lower temperatures. But what the catalyst really does is just changes that pathway through the reaction.